Welcome to this presentation discussing 5G production test considerations in a wafer test environment. My name is Daniel Bock from FormFactor. This presentation is going to go over some of the specifications for 5G and what are they driving in terms of wafer test specifications. We're also going to describe how can we design probe cards for the best isolation, in particular applying to RF front-end parts such as RF filters. We're then going to move on to what are the custom ISS products to match DUT layouts and how can we help provide the best RF calibration in a production environment. And finally, we're going to go through some of the recommendations on calibration settings where we will be able to provide recommendations on what calibration to use as well as what standards to use based on your test vectors as well as efficiency for wafer test as well as accuracy. In order to first understand what 5G is requiring in production tests, you need to understand what is 5G going to do in the market. 5G has been discussed over the past several years and has been characterized to be able to meet 4 primary application spaces. The first application space will be short-range use. These include personal smart devices like smartphones and smart watches and other tracking devices. Also, it will include smart buildings such as the Nest system for your thermostat in your house, as well as home security systems using cameras that are streaming to the internet. The next application is long-range use. This includes smart farming, where it will help to monitor plant generation, harvesting, and weather conditions, as well as urban monitoring that can look at air quality conditions, as well as traffic patterns. The next application is latency critical spaces. This includes autonomous driving, in which you need to have millisecond response for safety, as well as augmented reality and virtual reality services, which are video game as well as environmental type of augmentation systems, where if you have a long latency, it will create a very jarring experience in the use. The last place is industrial monitoring operations, where you need to be able to have rapid feedback in order to make sure that the industrial production is still within normal operating parameters. The last place is massive scale. This includes smart energy, where it will be monitoring the entire power grid network as well as redistributing the power as needed. And then smart mobility, which would be able to redistribute the network and loading of the various parts of the network as needed. Because of the new 4 application spaces for 5G, we are seeing that there will be a rapid growth in the number of IC chips that are being manufactured in the world. In particular, if you look at various devices, you can see why this is happening. Starting off with cell phones, even just working in the normal operating bands that have been around for many years, the channel aggregation is going to be increasing the number of filters as well as the number of switches and amplifiers in order to have the high MIMO requirements to meet the needs of the user. In addition, with the opening of the millimeter wave bands in the 28, 38, and 60 gigahertz, new millimeter wave components are going to be emerging over the next few years, such as the Qualcomm QTM-052 antenna in package. Not only are these going to be implemented, but because of the high loss factors of these as well as the sensitivity needed and bandwidth, each phone is going to have multiple antenna in packages in order to have a use that will make sense. In addition, the base stations in the infrastructure side are going to see up to a 6 times increase in the number of chips just to be able to handle the MIMO requirements at the LTE bands, as well as in the millimeter wave bands. The last component is going to be the short-haul backhaul application because of silicon photonics. In particular, coming out of the base stations, there's going to be fiber cables coming out and then going into the grander network, and this is going to need a very large increase in the number of fiber channels, not only because the number of base stations is increasing, as well as there being a lot more small cells being deployed in the world. In order to meet the challenging specifications of 5G, FormFactor has a wide variety of different engineering and characterization devices, all the way up to the full high-volume manufacturing production probe cards. In the engineering characterization space, we have analytic probes, including infinity probes, that are well met for the ability to be able to create device models and device extraction. We also have WinCal for RF calibration and RF measurement, as well as ISS standards that couple well with the infinity probes. Once we move over to production tests, FormFactor has several different probe card technologies that are very useful for RF. This includes the Piranha technology, Katana RF, as well as the pyramid probe technology, and FormFactor can help you choose the appropriate technology for your use case. In addition, we also have a standard suite of calibration standards that we can manufacture that will match your DUT layout. Now we're going to look at one particular example of 5G, which is the frequency range 1 filter requirements. Because of the increase in MIMO and spectrum proliferation, even at the sub 3 GHz bands, we're going to see a reduce in cost and size of filters. In addition, the requirements in isolation between filters, lower loss, and higher power handling requirements continue to create new challenges for the filters. If you look at the power chain below, you can see the biggest contributor to loss is the RF filter. This is very important to minimize the loss for total transmit efficiency, as well as to minimize the noise figure in the receive path. So in order to properly characterize these, that also means that the probe card is going to have the most accurate measurement to measure the loss in band, as well as being able to measure down to minus 70 dB out of band reject, which requires a probe card with isolation on that same order of magnitude. Based on many years of work with our customers, we have went through various experiments to figure out what is the best way to design a pyramid probe card to meet these very stringent requirements, in particular for isolation. In order to do this, we tried various different types of transmission lines, as well as different grounding schemes. On the very top one, you can see that's a standard design rule for us using a microstrip with a ground mesh. As you can see in the gray plot on the lower right, it's able to measure the in-band performance very well, but the out-of-band is not measuring as deep as the customer had required. And this is primarily due to ground inductance in the probe card. The next step is we made a microstrip with a solid ground, and as you can see in the orange chart, that has improved performance, but it's still not meeting the out-of-band reject level that they require. So finally, we did a final spin and redesigned it using 2 metal layers of ground surrounding the transmission lines. This improved signal-to-signal isolation dramatically, and we were then able to measure the minus 50 dB out-of-band reject of the RF filter. And this has now become part of our standard set of design rules when a customer tells us that they're going to be testing an RF filter with a pyramid probe card. The next part of production tests for 5G that is very important is how can you make sure you get the most accurate measurement in high volume manufacturing. In order to meet this need, we have developed a very large and extensive breadth of knowledge in how to do RF calibration for both filters and other RF SoC parts. Some of the things we can do for our customers is provide an impedance standard substrate that exactly matches the die layout. This is important so you can support multi-DUT calibration to reduce the number of touchdowns, as well as the ability to control the nearby sites on the probe card for RF impedance control to get the most accurate calibration, especially at the very low isolation levels that we are required to meet. In addition to the impedance standard substrate work we have done, we've also done extensive work of evaluating the different performance of different calibration methods with the pyramid probe card and the custom ISS. Here we show the comparison of different calibration methods of the pyramid probe card and the Piranha technology. We compared things including fixture de-embedding, automatic fixture removal, as well as the standard SOLT calibration method. We know the drawbacks and advantages of each method and when you should select the appropriate calibration method based on your test vectors, whether or not you're measuring just magnitude or a phase measurement, as well as the accuracy and return loss that you require. As we have discussed, FormFactor has experience in all of the different factors required for 5G production test, including RF filter measurement for high isolation, RF calibration, as well as what calibration method should be used. If you have any questions, please contact me or any one of our other applications engineers at FormFactor, and we can help you select the appropriate design for your 5G wafer test.